Okay, so in this section, we will learn how to represent functions in terms of power series. So last section, we learned about power series, and let me recall what it is. So power series has the form as follow. So this is the general form of power series. It has a coefficient Cn, and power series is depending on the variable x, center at a specific number a raised to some power n. So why are these things useful? Well, in this section, we'll learn that many functions can be represented in terms of power series. So here's our goal. So we'll show that many functions that you've seen in calculus can be represented. Okay. And the question is, why is this useful? Why do we want to take a function, let's say exponential function, natural log function, or trig function? Why do we want to take such function and represent it in this form? Okay, so why is this useful? So the point is, calculations with power series are generally easier and generally easier to encode it in your computer to do than putting the actual function. Let me give you an example. So this example. So let's say you pull up your calculator and you ask your calculator, find me the value for, you plug in natural log of 2 and ask your calculator, give me a decimal expansion for natural log of 2. Well, how do we input this? How do computer science input natural log of 2 in your calculator and make it understand what does it mean by natural log? Well, in reality, your calculator will use a power series to calculate any value of a natural log functions. So in your calculator, it will encode this power series. Instead of putting natural log 1 plus x, well, the calculator wouldn't understand what is natural log. But we can encode this power series. Okay. So for different value of x, so here if you want to find natural log of 2, you would put x equal 1 here. For different value of x, you see that this is just summing a bunch of fractions, and your calculator knows how to sum number. So in this case, for natural log of 2, So here x is equal to 2. Sorry, x is equal to 1. You put x equal to 1 here. So I get minus 1 to the n, and then x is 1, so I have 1 to the n plus 1 over n plus 1. So this is the series minus 1 to the n. 1 to the n plus 1 is always 1, so you have minus 1 to the n over n plus 1. This is nothing but the alternating series that we have been familiar with. And we can run through the alternating series test and show that this is convergent. If you list a couple of terms of this series, so I have n equals 0, so the first term would be 1, then the next term would be minus 1/2, plus 1/3, minus 1/4, plus 1/5, minus 1/6, etc. So when you ask your calculator to find natural log of 2, well, this is just an expression for the function. Your calculator actually carry out summing these fractions. So depend on the accuracy of your calculator. Say your calculator can display 10 decimal number up to accuracy. Then it will sum up to how many fractions here, such that it's within 10 decimal accuracy of the value of natural log of 2. Okay. So this is what your computer actually does when you ask it to calculate natural log of 2. So it's using power series to find value of functions. Okay. So here's our goal. So we want to write functions like these. For example, natural log, exponential as a power series. So this is one of the applications. Okay, so let's start with a fundamental example from what we know of power series. It's an important example. Okay, so if I have the functions as this simplest power series, center at 0, so it's just the power series x to the n. And we know that for each value, for a specific value of x, it becomes a geometric series. So we can use the condition for convergence of geometric series to say about the convergence and divergence of this power series. So geometric series is convergence as long as the common ratio is less than 1. So that means this power series has radius of convergence r to be 1. Okay. So this means that the magnitude of x has to be less than 1. Okay. And the interval convergence So this is center 0. Okay, radius of convergence is 1. So here's minus 1 and 1. So interval of convergence is from minus 1 to 1. And we cannot include endpoints because when x is 1, the series diverge. And we know that using the formulations of geometric series, if this series is convergent, so if the magnitude of x is less than 1, then we know the sum of this series is just 1 over 1 minus x. So we want to keep in mind this example. So let's say if I happen to see something of a fraction form, but instead of an x here, I have something else. So I would try to mimic this main example to express this as a power series. So here's the tips. So let's say instead of having an x here, I have some other expression of x. So let's call it u. Then we have 1 over 1 minus u is u to the n. Okay. And this is convergent for absolute value of u less than 1. Okay. Okay, so let's see in example how we use this to write functions that has similar looking as this one as the sum of power series, as a power series. Okay. So let's look at a couple examples. So express the following functions as a power series and find the radius of convergence. Okay. So let's say the first one is 1 over 1 plus x squared. Second one is 1 over 3 plus x. And third one is x to the 4th over 2 minus x cubed. Okay. How do I express these functions as power series? So if you look at this function, these have kind of the similar appearance as this function 1 over 1 minus x, though not exactly. So we have to make it looks to something like this. So we can use this expressions as a power series. Okay. So for the first one, so I have 1 over 1 plus x squared. So I know that if it's in the form of 1 minus u, then I can rewrite it as a power series. So this part is the same, this part is the same. It's just this part that looks different. So I will make this to be a minus u. Okay. So I would rewrite the plus x squared as 1 minus x squared. Okay. Now if I let my u be minus x squared, then this become 1 minus u. And we know before that this is the same as the power series u to the n, as long as u is less than 1. The magnitude of u is less than 1. Okay. So I'll look into the convergence of this later. Okay. So assuming the magnitude of u is less than 1, then we can rewrite this as this power series. Well, now we have to replace everything back into x, right? And u is minus x squared. So I'm replacing u equal minus x squared back in here. Okay. And then I have to clean it up so that it's in the form of power series. So power series, I need to have an x part, or x minus something part, raised to some power, right? So I'm going to pull out a minus 1 to the n, and this become x to the 2n. So the coefficient here is alternating between 1 and minus 1. This is the Cn. Cn is alternating between 1 and minus 1, and then you have a power series part. And this power series converge. Okay, so we managed to finish the first step, express the function as a power series. Now let's talk about the convergence of this power series. So this power series is convergent as long as the magnitude of u is less than 1. And then what is u? U is minus x squared, so we're going to put that in here. Okay, so minus 1 in the absolute value is just 1. So this is the same thing as absolute value. X squared is less than 1. So x squared is positive. You can bring the square out. So you have x absolute square less than 1. So if something square is less than 1, so both sides already positive. So that means this is true if you take the square root of both sides, you have x is lesser than square root of 1, which is 1. So this series converge when the magnitude of x is less than 1. So the radius of convergence is 1. this representation as a power series for this following functions. Okay. All right, so let's look at the second example. 1 over 3 plus x. So keep in mind that I always want to translate it back to the form 1 over 1 minus u. So somehow I have to translate this form to this form, okay? So the top is match up. The problem is the two number in the bottom doesn't match up. So let's take care of the 3. Well, how do I make the 3 to becoming a 1 here? Well, let's factor out the 3 so that we get the 1. So if I factor out the 3, this is going to be 1 plus x over 3. Okay. Now, this is just 1/3, so I'm just putting it into the front. So I have 1/3 times 1 plus x over 3. Now this part is looking more like the 1 over 1 minus u. Okay? And then whatever constant I have, I can just keep it in front and not touch it until the end. Okay, so I've taken care of this part, making it a 1. Now I want the minus u. So what do? I take 1 and I need the minus sign. So I need minus x over 3. Okay. So this is my u. Okay. So I let once I let u be minus x over 3, this expression becomes 1/3 times 1 over 1 minus u. Okay. So then we can use the formulation. 1 over 1 minus u is the power series u to the n for as long as the magnitude of u is less than 1. So 1 over 1 minus u is sum of u to the n, and from 0 to infinity for magnitude of u less than 1. Okay? And then we can replace the expression of u in terms of x back to the series. Okay, and then I clean it up. So I have a minus 1 to the n. Okay, usually if you have a multiplication, division, you just split things up. And then x to the n. Okay. So this becomes the power series. Minus 1 to the n, and then I'll combine this 3 and this 3 to the n to 3 to the n plus 1, x to the n. So this is in the form of power series. This thing is your Cn coefficient. This is the power of x part. Okay. And this is exactly the representation of this function. As long as we have the magnitude of u less than 1. So this will determine this will determine our radius of convergence. So let's look at this. So this series converge when u is less than 1. And what is u? Well, u is minus x over 3. Okay. And then minus in the absolute value become plus. So I have 1/3 x less than 1. So that means x is less than 3. So my radius of convergence would be 3 here. Radius. Okay. Now let's look at the last example. Okay, this looks a bit tricky, okay, because it looks like everything is different from the form 1 over 1 minus u. So somehow we have to translate it to looking like this. Okay, let's look at the top part. So I want this to look like 1 over 1 minus u. Okay. Well, the top part doesn't have 1. It had x to the 4th. So how do I get 1 from x to the 4th? Well, let me just factor out the x to the 4th. So then this becomes x to the 4th times 1 over 2 minus x cubed. Okay? Now it's looking more like this, at least for the top part. Now we're taking care of the 2. Well, like the last example, we just factor out the number here to make it into 1. Okay? So I will factor out 2. Okay. Now these are just coefficients in front of my expression. So I will clean it up at the end. Okay. So now this expression right here is looking more like the expression that I can rewrite it as a power series. Okay. So from here we can let u be x cubed over 2. Then we can use what we know of the power series, 1 over 1 minus u. So this becomes 1 minus u. So it's equal to the power series u to the n. Well, now I'm going to plug the expression of u in terms of x back in. So this becomes x cubed over 2 raised to the n. So this is x to the 4th over 2. And then I'll clean things up in this step. So this is x to the 3n and 2 to the n. Okay, and then I'll combine the like terms. So this is x to the 3n plus 4. And down here is 2 to the n plus 1. And this is the series representation for our function x to the 4th over 2 minus x cubed, as long as the magnitude of u is less than 1. Okay, as long as we have the convergence for this power series. Okay, so now let's determine the convergence. So this means the magnitude of x cubed over 2 has to be less than 1. So this means x cubed is lesser than 2. Okay, now take the cube root of both sides. You have magnitude of x lesser than cube root of 2. Taking cube root of both sides. So that means my radius of convergence r will be cube root of 2.